Hello, welcome to this discussion of our chapter 3 of complex variables, volume 1. Our today's discussion is about absolute modulus, known magnitude of a complex number. These four words have the same meaning. So in case you are asked to find the absolute, it is the same as to find the modulus, it is also the same as to find the known, and it is also the same as to find the magnitude of a complex number. So absolute modulus, known magnitude of a complex number, can be obtained from the following. If z is equal to x plus iyy, then its absolute value is given by absolute value of z is equal to the square root of x squared plus y squared. So how do we get x squared and y squared? This x squared is the real part of this complex number, and this y is the imaginary part of this complex number. So to get the absolute value of z, just take the square root of its real part squared plus its imaginary part squared, which is x squared plus y squared. Also, if we have z1, z2, z3 up to zn, and these numbers are complex numbers, then the following properties are true about them. Number 1, the magnitude of z1, z2 is equal to the magnitude of z1 times the magnitude of z2. Or, the modulus of z1, z2 is equal to the modulus of z1 times the modulus of z2. Therefore, the modulus of the product is equal to the product of the moduli. Also, if we have the modulus of z1, z2 up to zn, this is equal to the modulus of z1 times the modulus of z2 times that's the modulus of zn. So that is the first property for a complex number, for the modulus of the complex number z1, z2, z3 up to zn. Then also, number 2, the modulus of z1 divided by z2 is equal to the modulus of z1 divided by the modulus of z2, provided z2 is different from 0. So z2 must be different from 0. Because the moment it is 0, the whole of this term will be undefined. Then lastly, the third property is that a modulus of z1 plus z2 is less or equal to modulus of z1 times plus modulus of z2. Also, the modulus of z1 plus z2 plus that's zn up to zn is less or equal to modulus of z1 plus modulus of z2 plus that's modulus of zn. So let's look at some worked example under modulus of a complex number, or absolute value of a complex number. If we have this question, find the absolute value of z is equal to 3 plus 4i. And so in this question we are tasked to find the absolute value. So this can be obtained if z is equal to x plus iyy, then its absolute value is given by the absolute value of z is equal to the square root of x squared plus y squared. So our task is to identify x and y in this complex number. So our value of x is 3 and our value of y is 4. So it will be a matter of substituting 3 here and a matter of substituting 4 here. So this means that therefore the absolute value of z is equal to 3 plus 4i will be absolute value of z is equal to the square root of 4 squared plus 3 squared, which is equal to square root of 25, because this will be 16 plus 9, which gives us 25, and this the square root of 25 is 5. And since we are taking the absolute value, we shall only consider the positive. For the case of the absolute value, we don't consider the, remember when you take the square root of a number, you have a positive and a negative. But the moment we take the absolute value, we shall only consider a positive 5. And this can also be worked out using or by first presenting the complex number on the Gantt diagram. So here we present z is equal to 3 plus 4i on the complex plane or Gantt diagram, and this can be done by identifying the real coordinate and imaginary coordinate, whereby our real coordinate is 3 and the imaginary coordinate is 4. So we shall plot 3, 4, where we shall have it at this point, and the absolute value will be the distance from the origin up to the plotted point, which will be this distance will be the absolute value of z. Now, if you have to find this distance from the origin up to the plotted point, since this is a right angled triangle, we can use Pythagoras theorem, which states that the distance from this point up to this point square is equal to the distance from this point up to here, which is y squared, plus the distance from here up to here, which is also x squared. So we shall have the z squared, absolute value of z squared is equal to x squared plus y squared. So to find this distance, we take the square root both sides, which will take us to the absolute value of z is equal to x, the square root of x squared plus y squared. So we already have the value of x squared, which is 3, the value of x is 3, and the value of y is 4. So we shall have 3 squared plus 4 squared, which will be the square root of 25, and this gives you 5. So we can first present this on the Gantt diagram, and then we find the distance from the origin up to the plotted point. Then that is done by using Pythagoras theorem, and that would be equivalent to the absolute value of that complex number. We have some exercise which you can try at home. Find the magnitude of the following complex numbers. Number 1, z is equal to minus 3 plus 4i. Number 2, z is equal to minus 5 plus 12i. Number 3, z is equal to 7 minus 8i. Number 4, z is equal to 2 minus 6i over 3 plus 2i. And Roman 5, z is equal to 4i divided by 1 plus 5i squared. So try these numbers while at home, so that in the next lecture you presents them. He presents the answers of these questions. Let's look at some more examples. Using the method of complex conjugate of a complex number, so that the absolute value of z1, z2 is equal to the absolute value of z1 times absolute value of z2. We had saw this by using the method of complex conjugate. So, from the method of complex conjugate, we know that if you have z times its complex conjugate is the same as having the magnitude of z squared, or absolute value of z squared. And this can be clearly be shown on this side, where we have z times its complex conjugate. We shall have this x plus iyy times x minus iyy. This will be x squared minus iyy, ixy plus ixy, then minus I squared y squared, whereby I squared is negative 1, so when we substitute we shall have positive y squared, which is here, and these two terms will cancel. Then we shall remain with x squared plus y squared. And remember, the whole of this is the same as the magnitude of z squared, which is here. So if you have z times its complex conjugate, shall have the get the magnitude of z squared. So it can also be shown here that the magnitude of z squared is equal to x squared plus y squared. So this means that if you also have the magnitude of z1, z times z2 squared is equal to z1, z2 times z1, z2 its complex conjugate, whereby z1, z2 represents by z here, and z1, z2 complex conjugate represented by this. Then the next step here is that absolute value of z1, z2 squared will be equal to, this is z1 times z2 into complex conjugate of z1 times complex conjugate of z2. This is done by substituting z1, z2 complex conjugate, which is equal to z1 complex conjugate times z2 complex conjugate. So if we substitute the whole of this one here, we shall come up with this expression. Then the next step will be, remember we said that z1, z2 is the same as z1 times its complex conjugate is the same as z1 squared. Then z2 times its complex conjugate is the same as z2 magnitude squared. So this implies that absolute value of z1, z2 squared is equal to the absolute value of z1 squared times the absolute value of z2 squared. This is done or got by substituting z1 times its complex conjugate, which will give us z1 squared, and z2 times its complex conjugate z2 will give us the magnitude of z2 squared. Then after here, to get our final proof, we shall take the square root both sides. So taking the square root both sides, we get the square root will cancel with this, and will cancel with this. So we shall have magnitude for absolute value of z1, z2 equal to absolute value of z1 times absolute value of z2. So we have exercise also here that you can try it while at home, and you present in the next discussion. Using method of complex conjugate of a complex number, show that Number 1, the absolute number of z1 over z2 is equal to the absolute number of z1 divided by absolute value of z2, provided the absolute value of z2 is different from 0. Then number 2, the absolute value of z1 plus z2 is less or equal to absolute value of z1 plus absolute value of z2. Also, the following properties are true about the conjugate of complex numbers. For z complex number z1, z2, we shall find that the complex conjugate z1 times z2 is the same as having the complex number, the complex conjugate of z1 times the complex conjugate of z2. Then property number 2 is that if you have z1 plus z2 and you conjugate after adding, is the same as have the complex conjugate of z1 plus the complex conjugate of z2. Then finally, we shall find that if you have a complex number and you take the complex conjugate twice, you go back to the original complex number, which will be z. Let's look at some worked example. This is example 1. If you are required to show that the conjugate of z1 plus z2 is equal to the conjugate of z1 plus the conjugate of z2, this can be done if we let z1 is equal to x1 plus iy1 and z2 is equal to x2 plus iy2, then z1 plus z2, we shall substitute the value of z1 here, which is x1 plus iy1, and z2, which is x2 plus iy2. So we shall have this expression. If we correct like terms whereby the real parts come together and the imaginary parts come together, we shall have x1 plus x2 plus I into y1 plus y2. Then if we take the complex conjugate of this expression, we shall just interchange where we have a positive, it becomes a negative. And we only interchange on the imaginary part. You don't change anything on the real part. It's only the imaginary part, when you are taking the complex conjugate of a complex number, that changes the sign. So if we change the sign of I imaginary part here, we shall have minus. So we shall find that the complex conjugate of z1 plus z2 is equal to x1 plus x2 minus I into y1 plus y2. So if we open the brackets here, we shall have x1 minus iy1, which will be here, and then here we shall also have x2 minus iy2 after opening this bracket and bring this term here and this term here. So we shall find that this is automatically the complex conjugate of z1, and this one is also automatically the complex conjugate of z2. Then finally, we shall have the complex conjugate of z1 plus z2 being equal to the complex conjugate of z1 plus the complex conjugate of z2. And this will take us to our proof that was required to be proved. So meaning that z1 plus z2 complex conjugate is equal to z1 complex conjugate plus z2 complex conjugate. Then example number 2. show that the conjugate of z1 times z2 is equal to z1 complex conjugate times z2 complex conjugate. So if we let z1 is equal to x1 plus iy1 and z2 is equal to x2 plus iy2, then we shall find that z1 times z2 is equal to x1 plus iy1 into x2 plus iy2. This is done by substituting the value of z1 and z2. Then the next step, we open the brackets here, because we earlier saw how to open the bracket if you have two complex numbers multiplied together. So we shall have this expression, and find this, the complex conjugate of z1 times z2. We shall go ahead and change the sign on the imaginary part, which will be minus I. Then the next step is to correct like terms. So we shall have x1, x2 coming with minus x1, y1, and minus y1, y2 coming to with minus x2, y1. So we shall have this step here. Then we shall find that in here we can pull out x1, which will be x1 into x2 minus iy2, and also here we can pull out iy1, which will be minus iy1 into x2 minus iy2. Because if we open here, it will become I squared, which will create a positive here. Then finally, we shall factor out x2 minus iy2 since it is common. So we shall remain with x1 minus iy1 into x2 minus iy2. And this is equivalent to the complex conjugate of z1, complex conjugate of z2. So finally, we shall have the complex conjugate of z1 times z2 being equal to the complex conjugate of z1 times the complex conjugate of z2. Then we have another exercise here that you can try it out. Show that the conjugate z double bar is equal to z. So here you are required, so that if you have a complex number and you take its conjugate 2 times, you will go back to the original expression of that complex number. So you try it out. In the next discussion, you present it as before we start our presentation. So thanks for watching this video, and our next discussion will be on polar representation of a complex number. And also remember to subscribe my video on YouTube.